Alright, so here we are with the last student project. This started out life as an inkjet printer, and we tore it apart, and you can see the carriage here that's supposed to hold the inkjet cartridge. There's a linear carriage that goes back and forth. The stepper motor, you can actually see the output gear right there. The stepper motor itself, I'll try to get a shot of the back side of it. You can see it here a bit. And it is a 4-wire stepper motor. So this group had an amazing challenge, and they actually overcame it and did a great job. The problem with a 4-wire stepper is that you've got to reverse the polarity on the phases. And we don't have that ability on the professional development board. So you notice this is the one group that is not using the driver chip on the board. They're using the circuit that they found, actually the chips from the circuit they found in the printer itself. There was a board mounted on the back side. They figured out which chips were the actual driver chips for the 4-wire stepper motor, pulled them out, looked them up, got a data sheet, found a sample circuit, actually built that circuit here on the perf board, and I will include the circuit itself as well as the data sheet for these chips. They just used the sample circuit, built it, got it working, and are driving their 4-wire stepper motor with these custom chips. They also had to look at the phase diagrams in the data sheet for these chips as well to see what the appropriate outputs were to turn on in order to drive this stepper motor through the chips. So they had to figure out timing diagrams as well, which was a good experience. One more feature of this system, as the Daisy, as in the, not the Daisy, but the dot matrix printer, there's a homing switch, but this one is a infrared homing switch. There's a detector and receiver. They had to figure that out as well, and you see this connector here that I'm zooming in on that has a red, green, and black wire. They had to figure out how to use that to sense the flag on the back side of the carriage. You probably can't see it in the shot. There's a flag on the back side that when the carriage comes over here, it trips that black sensor. You can see it there. I'm panning around it. Anything else I've missed at this point?
Have it go home.
Okay, so when they reset the system, what happens is it automatically goes back to find the home position. And we've assumed, or they've assumed in the code, that home is always in this direction. So the carriage has to start off to this side of the flag. If it starts off over here, it doesn't work properly. It just keeps trying to go in that direction. But since that wasn't the focus of the experiment, the focus was driving the stepper motor, we left it at that. And when you reset the code, what happens is it finds home, and then it goes to the current command position of the potentiometer. As you change the potentiometer position, the carriage tracks that position, that command position, and moves back and forth. This is one of the faster circuits or faster stepper motor drivers because the chips are made to perform what we believe is called clipping or chipping to drive the motor even faster. So, system works well. You can see the LEDs. If you'd move it again, please. You can see the LEDs cycling, indicating the phase information that's being sent into the circuit. Notice there's a key difference here. Thank you. The LEDs on this board represent the command input to the driver chip, whereas on the other boards, the LEDs represent the actual outputs to the phases. Since these phases get reversed, then you can't represent that very easily with the LEDs. So, anything else?
No.
Okay, thank you guys. Good job. They had a very hard system because they had to build this circuit. That was the only way they could drive this stepper motor. So they challenged it and succeeded.